Welcome back. Previously, we had taken a look at magnets and had discovered that electricity flowing through a wire can actually create a magnetic field. Now, in a wire, we've discovered that the magnetic field's direction was given by the right-hand rule, where the thumb pointing in the direction of the current, the fingers would curl in the direction of a magnetic field around a long, straight wire. Now, we looked at a couple of different geometries for that, a long straight wire, a loop of wire, or a solenoid, which is a stacked series of loops that is longer than it is wide. Now, let's take a look at the magnetic field strength, or the magnetic field, the magnitude of the magnetic field at those locations, or in those geometries. Now, for a wire, I mentioned that the field decreases as we get further away from the wire. The magnetic field decreases. Now, that relationship we've shown is actually an inverse relationship. It's 1 over that distance. We can also show very easily that the current flowing is proportional to the magnetic field. Doubling the current would give you double the magnetic field at some distance away. So, that equation, the proportionality to the current and the inverse proportionality to the distance, gives us an equation where the magnetic field, which is denoted with the symbol capital B, right? That symbol, capital B, is equal to the vacuum permeability, which is this mu naught. Just like there is an epsilon naught, the vacuum permittivity, which talks about how easy or how well an electric field can be established in vacuum. This is how well a magnetic field can be established in vacuum. It's often called the or the magnetic permeability of vacuum, or the vacuum permeability. That value, until very recently, was defined as 4 pi times 10 to the negative 7 in standard SI units. But it's now, because of the redefinition of the kilogram and all the associated units with that kilogram, it is now an experimental unit measurement. It needs to be experimentally determined. And that's our task for today in just a little bit. Now, if we have this magnetic field, B, right, we can say it's equal to mu naught multiplied by current, I, divided by 2 pi r, where r is the distance away from the wire you are, or if you're looking at a circle, because the magnetic field exists in these circular loops, it's the radius of that circle away from that current carrying wire. So B equals mu naught times I over 2 pi r. Now, if you were to take a loop of wire, so take that same wire, pass a current through it, and loop it, then in the center of that wire, you'd actually have a stronger magnetic field because there is a more contribution from each of the parts of that wire. So the magnetic field strength at the center of a loop of wire is equal to mu naught times I divided by 2r. We've dropped the pi. It's pi times stronger, and that shows up because of the geometry here and the fact that we're using calculus. The details we can't go into right now for this course, but trust me, it's 2 pi times r. Now, or 2i, sorry, not 2 pi times r, just 2r. Now, if I were to make a second loop, I would effectively have twice the current, and so I would have twice the magnetic field strength. A third loop would give me 3 times the current in that area, or 3 times the magnetic field strength. And so we can actually end up adding a capital letter N for the number of turns, or number of coils, into that numerator. So B is equal to mu naught times N times I over 2R for a stacked series of coils. So coil wire, many loops, there, we get that value. If we were to continue stacking those coils and turn out to a nice long solenoid like this one, then what we get is a magnetic field on the inside equal to mu naught times N times I divided by L, the length of the coil. This is the length of the solenoid, the physical length measured in meters. Notice that the radius of the solenoid doesn't play a role here. Just like in electric fields between 2 parallel plates, the distance between them didn't make much of a difference at all. It was only the area of the plates that made a difference. You could change the distance between the plates and you have the same electric field. You change the size of a solenoid, as long as you don't change the number of coils, the current, or the length of it, and you can have the same magnetic field on the inside. Now, The requirement for a solenoid is that it has to be much longer than it is wide, and so that is satisfied with this air-filled solenoid here. Now, technically, we are not in vacuum. We are in air. I can breathe it. And so we're not talking about the vacuum permeability mu naught specifically. We're talking about the magnetic permeability of air. But the two values are less than 4/10,000ths% difference. Maybe even 400, 10 to the negative 5, 100,000ths%, 400,000ths% difference. So we can be reasonably sure that if we are measuring one value, we're measuring the other. All right, so our activity today is to use this setup right here to determine an experimental value for that vacuum permeability, that mu naught value. Okay? Now, I have a solenoid attached to a power supply with a switch and a resistor, so I can run a current through it. I have a Vernier branded current sensor here, which is communicating with graphical analysis on my iPad. I also have a magnetic field sensor, also by Vernier, which is communicating with my iPad in graphical analysis. So I'll be reading the two values there and being able to control the current with my power supply and measure the value of current and associated magnetic field inside the solenoid as I do so in real time. I'll be able to measure both of those values and use them as the independent variable, current, and the dependent variable, magnetic field strength, to determine how that relationship is, to verify, first of all, that it is proportional, and that the constant of proportionality, the slope, should be equal to n times mu naught over L. If I can count the number of coils in this loop, or the solenoid, 520, by the way. There are 5 layers, and each layer has 104 loops. I counted. I did. 104. And then if I measure the length of it and determine it's 149 millimeters, so 0.149 meters, then I should be able to determine an experimental value for the magnetic permeability of vacuum, that mu naught. So let's get started. I'm going to throw the switch, start collecting on my iPad in graphical analysis, and I'll show you these values so that you can pause the video at intermittent times to write down some values and produce your own graph. From that graph, you should be able to determine the experimental value for the magnetic permeability of vacuum, or that mu naught. All right, so I'll hit collect. Our sensors are zeroed. We'll start data collection by throwing the switch, and then I will slowly raise the current by raising the voltage. I'll pause every so often so that you can get a new reading off of it once it stabilizes a little bit, and allow you to record these values as we go. You know, 1 amp is about as high as we can go with this current sensor. All right, so hopefully you're able to record a bunch of values there, and you'll be able to use those to generate your own graph and determine your own value for the vacuum permeability, mu naught, a fundamental constant of the universe. Combine that with epsilon naught, and you can calculate the speed of light. All right, enjoy.